Okay, welcome back. Last time we looked into some of these bounds for information measures. In particular, I want to point out is this conditional conditioning reduces entropy. Basically, hx given y is less than equal to hx. So whenever we know a little bit more about a related random variable, the remaining information will be less. So this is kind of intuitive, but immediately it would be tempting to have an analogy that is a equality. There's a question I brought out last time. Basically, will we also have like ixy, the mutual information between x and y, will be bigger than or equal to ixy given z? It turns out that this is incorrect. This is not possible. I mean, in the sense, of course, sometimes you can find cases like that, but in general, it's not true. So in general, it can go both ways. And actually, we can easily see why it can be so, because on the left-hand side, if I have ixy equal to 0, basically it's the condition that x is independent of y. On the right-hand side here, this will be equal when x and y are independent given z, right? So, in general, these two conditions are not related in the sense that one does not imply the other and the other way around. I guess here maybe it probably helpful for us to go a little bit deeper to discuss like independence and conditional independence. I find that like at least for myself, I was confused at the beginning for these two relationships. So, but turns out they're actually quite simple if you think of that. Independence, okay, as you already know, basically, the condition for xy to be independent is the joint distribution of x and y can be decomposed into px, py. And for conditional independence, it's basically we have this conditional probability pxy given z. Conditional distribution can be decomposed into px given z and py given z. So basically, for the independence condition, we are looking into the marginal distribution that can be decomposed into multiple components. But here we are looking into the for conditional independence, we are looking really into probability that given a parameter, you can think of like when the distribution is parameterized by something, another variable, that a parameterized distribution can be decomposed. So I guess it will become clearer if I also, for this independence case, I introduce another variable c here. So, for example, if I have a independent x and y here, and let's say z is a kind of variable that may depend on x and y. So then the joint distribution of x, y, and z, actually, as long as x, y are independent, in general, in general, I can always write like this, right? Z given xy and pxy. And I have this is equal to b z given xy px py. This is because x and y are independent. Now, what we can see here is, or like we can think of like here is, we have this condition is basically considering the marginal distribution of pxy, or I should say marginalize the joint distribution xy z over z. I guess I will use summation, even though I can have z is continuous. Let's just think of all these variables as discrete. So xy and z. If I sum over z, I suppose to get pxy here, and then like because this xy is actually constant here with respect to z, I can plot pxpy here, and xy here is more or less like some parameter. So it's itself here is just think of it just a distribution of a single variable z here. The only difference is like for different xy, I basically have different distributions. So therefore, what I mean is like xy is kind of parametrizing. It's difficult to pronounce. Parametrizing this distribution z, and because if basically it's just a distribution of a single variable z, if I sum over z, basically this will get in 1. Of course, I'm just going backward. Of course, I know at the beginning this should be give me pxpy. But from here, we also see something is interesting, because if we write like this original distribution now, the joint distribution, not the original, the joint distribution of x, y, z, if I do not marginalize it, I mean in the sense that I observe z. Now if I observe z, then I will have z is equal to some particular, let's say z0 here. Then the distribution I'm looking at is really some px, y, and z0, right? And that will be something like p z0 given x, y, px, py. And now I can no longer decompose this distribution into some form like px something and py something, or px z0, py z0, in the sense that the first factor only depends on x and the second factor only depends on y. And that's why you see like why this is not conditional independence, in the sense that like if I know z, I break the independence. It's not just like at the beginning I'm independent, but after I observe z, now I'm no longer independent x and y, because now I cannot split this joint distribution px, y, z0 into some px z0 and py z0 anymore. That I cannot do. And sometimes like people explain this more intuitively to use like to say some the phenomenon is known as explaining away. Basically, if we know the outcome of this guy here, then these two variables are no longer independent, because if both of case, one typical example is like you observe let me just give an example, x, y, and z, and z is like the ground is wet, and you have this label, basically water the front yard, and you don't know, you assume this is a probabilistic event, you don't know when the labels will come up and water is garden and so on, and basically it rains. So in general, these two events, let us assume this to be independent. Of course, in a case you can argue that like if it rains, your labor is not likely to water the garden, but in any case, for for this case here, like just for the convenience of explaining this idea, let's just assume that x and y are independent. These two events are independent. But both of them will lead to an outcome is basically the ground will likely to be wet. And at the beginning, if I don't know the ground is wet or not, this is basically independent. But if it turns out I see the ground is wet, then actually it's kind of explaining away in the sense that if I know the labor also water the garden, then the chance of raining will become smaller. Just because that I also know that the ground is wet. If I don't know the ground is wet, then basically these two events is totally independent. But if I know that the ground is wet, then it actually, whether it rains or not, of course, it rains or not is what I mean is I rained in the morning, let's say, and then I come back from work and then I observe whether the ground is wet or not. Let's say I also don't know whether it's actually rained, and like I don't watch the TV or like news and so on, and I just want to know whether it rained or not in the morning. And then if I observe that the ground is wet, originally I will think that it's quite likely it has rained, right? But if I already also know that if the labor have watered the garden in the morning, then it will explain away this event here, then the chance of raining in the morning will be smaller. Okay, I'm sorry, I mean like here, I guess I'm not very much organized. But again, this event here is basically x is labor. Okay, everything is happening in the morning, let's say morning, and this is in the morning also. And this, I'm observing that in the afternoon or like when I go back in the evening. So what I want to know is that whether in the morning it actually got my labor watered the garden, and also like whether it rained in the morning. And for both events at the beginning, they are assumed to be independent. But now, if I know that the ground is wet, and I know that my labor watered the garden, then the chance of raining in the morning will become smaller. And of course, like if my labor didn't water the garden, just the opposite, that the chance of raining will become higher if I observe that the ground is wet. So therefore, like this gives kind of interesting example that like whenever we observe something, it can actually affect the dependence or independence of variables that is kind of related to your observation. So, okay, this is for the one that is original independence. And let's look at another example that's the other way around. Let's say we have this z variable here, that x and y are conditional independent. So basically x kind of depend on z and y kind of depend on z, but they are not kind of depend to each other like directly. In the sense, if I write the joint distribution, it would be like this. Yeah, it's like this actually. This p x y z is equal to p z p x y given z, but I also have this conditional independence condition here. So I have this p x y z is given equal to p z, p is given z, py given z. And now what I want you to see is that this in general will not lead to the independence condition. Basically, if I try to find the marginal distribution of this guy here, let's try to marginalize it. How to marginalize this will be basically pxy is just equal to pxy z sum over z, right? But in this case, as you can see, because this z here is kind of coupling with this pc here, these two terms is coupling with these terms here, we cannot really do any kind of simplification here that basically in any case I cannot write this eventually into some px multiplied by py. So therefore, like, even though like given a z here, I can write that they are independent, but when I try to marginalize it, I don't have pxy is equal to pxpy. So actually this is exactly the opposite of this case we discussed earlier here. In this previous case, basically we have random variable originally that are independent, and if we observe something related to this variable now become dependent. In this opposite case, basically we have this random variable are basically not independent, but if we observe something, they will become independent. For example, if let's say I actually observe z is equal to z naught here, so then I can basically just think of like now the distribution is just z naught, and think of z naught as just a parameter, and therefore I can really decompose this distribution into px given z naught and py given z naught, and the first factor only depend on x and the second factor only depend on y. I guess that's it's more like it. Maybe next time I will try to give an example, or hopefully we'll make it a little bit more concrete.